Imagine a world where traveling to distant stars is not just a dream, but a tangible possibility. The key to this future lies in a concept that has captured the imagination of scientists for decades: nuclear fusion. The same process that powers our sun, fusion holds the promise of a near-limitless source of energy, but the potential of nuclear fusion goes beyond providing clean energy on Earth. It could revolutionize space travel, enabling spacecraft to travel faster and further than ever before. The sun's heartbeat. At the core of every star, including our sun, nuclear fusion takes place. It's a process where hydrogen nuclei fuse under extreme pressure and temperature to form helium, releasing vast amounts of energy. This reaction is the foundation of the sun's immense power, providing the energy that sustains life on Earth. For centuries, scientists have been fascinated by this process, eager to replicate it here on Earth as a clean energy source. But what if this very same process could power spacecraft and take us across the stars? The principles behind nuclear fusion are simple in concept but extremely challenging in practice. For fusion to happen, hydrogen nuclei must overcome the natural repulsion between their positively charged particles. This requires temperatures that can reach millions of degrees Celsius, conditions typically found in the cores of stars. However, if we can master these extreme conditions here on Earth, the implications for space travel are mind-boggling. The vision of fusion propulsion. The concept of nuclear fusion as a propulsion system for spacecraft could change everything. Traditional chemical rockets are limited by the amount of fuel they can carry and the short bursts of energy they produce. To travel to distant planets like Mars, astronauts endure months of travel. But with nuclear fusion propulsion, spacecraft could achieve near-light-speed travel, drastically reducing the time it takes to reach our neighbors in the solar system and even other star systems. Imagine the possibility of a spacecraft accelerating continuously instead of relying on short bursts of fuel. This is the potential of fusion propulsion. By using the energy produced by fusion reactions to heat a propellant, such as hydrogen, and expelling it at high speeds, spacecraft could reach unimaginable speeds. This continuous acceleration is a key feature that chemical rockets simply cannot provide. A sustainable fuel source for the stars. One of the most intriguing aspects of nuclear fusion for space travel is the fuel source itself. Fusion propulsion relies primarily on isotopes of hydrogen, specifically deuterium and tritium. These isotopes are relatively abundant and can be extracted from seawater. Tritium, although rare, can be bred from lithium, a material also available on Earth and possibly on the Moon or asteroids. This raises a compelling question. If we can create fusion reactors in space using these readily available fuels, we could drastically reduce the amount of material we need to launch from Earth. This would make deep space exploration not only possible, but sustainable. The ability to use fusion as a source of propulsion also means we are looking at a future where space missions could be fueled by the resources already present in space, such as water or lithium-rich asteroids. This approach could eliminate the need to constantly launch fuel from Earth, which would reduce costs and make long-term space exploration far more feasible. Challenges of fusion on Earth. However, the dream of harnessing nuclear fusion is not without its obstacles. Achieving controlled nuclear fusion on Earth has proven to be one of the most significant scientific and engineering challenges of our time. For fusion to take place, scientists need to create the extreme conditions that exist in the cores of stars. These conditions, high pressure and temperature, are not easy to replicate. Projects like ITER, International Thermonuclear Experimental Reactor in France, are at the forefront of this effort. ITER is a multinational collaboration aimed at creating a functioning fusion reactor. If successful, ITER could pave the way for similar technologies to be applied to space travel. Scientists and engineers are working tirelessly to develop fusion reactors capable of sustaining the reactions needed for power generation and propulsion. Yet, the technical hurdles remain immense. Fusion propulsion. In space. The future of travel. One of the most exciting aspects of fusion propulsion is the potential to revolutionize how we travel in space. With fusion, spacecraft could travel vast distances across our solar system in a fraction of the time it would take using current chemical propulsion methods. For example, a fusion-powered spacecraft could reach Mars in just a few weeks instead of the 6 months it currently takes with conventional rockets. This breakthrough would not only open the door for crewed missions to Mars, but also to distant asteroids, the outer planets, and beyond. Moreover, the energy produced by fusion reactions is millions of times more powerful than chemical reactions. This means that with just small amounts of fuel, fusion-powered spacecraft could travel vast distances. The idea of interstellar travel, visiting other star systems, suddenly becomes a tangible possibility. Concepts like the fusion rocket have already been proposed, where the energy from fusion reactions would be used to expel propellants at high speeds, generating continuous thrust. The fusion rocket. Breaking through limits. One of the most promising designs for fusion propulsion is the fusion rocket. In this concept, the energy generated from fusion reactions would heat a propellant like hydrogen, expelling it at high velocities to generate thrust. Unlike traditional chemical rockets that rely on burning fuel in short bursts, a fusion rocket could maintain continuous acceleration. This means spacecraft would be able to travel much faster and more efficiently, reducing travel times for missions to the far reaches of our solar system and even to other star systems. The ability to maintain continuous acceleration is what sets fusion propulsion apart. With current chemical rockets, once the fuel runs out, the spacecraft must coast, relying on momentum alone. But with fusion propulsion, the spacecraft could keep accelerating, reaching speeds that could one day make interstellar travel a reality. As we look beyond our solar system and envision humanity's future in space, nuclear fusion propulsion becomes not just a dream, but a potential game changer. Imagine a future where interstellar travel is no longer a far-off fantasy, but a reality within reach. If scientists can successfully harness nuclear fusion for propulsion, it could redefine how we explore the cosmos, making deep space missions feasible and even routine. Reaching for the stars. Interstellar travel. Interstellar travel has always been one of the most alluring ideas in the realm of science fiction. The idea that we could one day visit distant stars, explore other solar systems, and even colonize exoplanets in faraway galaxies seems unimaginable with current technology. Conventional chemical rockets, which power our current spacecraft, simply don't have the capacity to reach the stars within a human lifetime. The distances between stars are simply too vast, and even at the speeds our best rockets can achieve, a journey to the nearest star, Alpha Centauri, would take over 70,000 years. This is where nuclear fusion comes in. With the ability to generate vast amounts of energy from small amounts of fuel, fusion propulsion could allow us to reach a significant fraction of the speed of light. At just 10% of the speed of light, a spacecraft could reach Alpha Centauri in just over 40 years, a time frame far more reasonable for human exploration. If a spacecraft could achieve higher speeds, say 50% or more of the speed of light, trips to even the farthest reaches of the Milky Way would no longer be beyond our reach. The dilemma of fuel. Harnessing fusion in space. One of the critical advantages of fusion propulsion in space is the fuel itself. Unlike chemical rockets, which rely on the combustion of fuel such as liquid hydrogen or kerosene, nuclear fusion uses hydrogen isotopes, deuterium and tritium, as fuel. Deuterium can be extracted from seawater, and tritium can be bred from lithium, which is also abundant on Earth and even on the Moon or asteroids. This makes fusion propulsion far more sustainable for long-term missions, especially when compared to the finite resources required for chemical rockets. This advantage becomes even more compelling when we think about the long-term future of space exploration. With fusion, spacecraft could travel across the solar system with a small amount of fuel, drastically reducing the need to carry large quantities of propellant. For deep space missions, this would be a game changer, as it could allow for much longer missions, whether for research or colonization purposes. For example, Consider the prospect of a mission to the outer planets of our solar system. Like Neptune or Uranus, current chemical propulsion methods would take years just to reach these distant worlds, and even then, the spacecraft would be limited by the amount of fuel they can carry. With fusion propulsion, however, the spacecraft could travel farther and faster, making the outer edges of the solar system much more accessible. Fusion rockets, the next step in space travel. One of the most practical designs for nuclear fusion propulsion is the fusion rocket. In this concept, the energy released from fusion reactions would heat a propellant, like hydrogen, expelling it at extremely high speeds to generate thrust. This thrust could potentially propel spacecraft at much higher velocities than conventional rockets, allowing them to achieve speeds that were once thought impossible. A fusion rocket would function quite differently from today's chemical rockets. In traditional rockets, fuel is burned, producing high-pressure gases that are expelled out the back to create thrust. But fusion rockets would rely on the release of energy from nuclear reactions, specifically the fusion of hydrogen isotopes. The energy generated from these reactions would heat a propellant, which is then expelled out the back at incredible speeds, generating thrust. Unlike chemical rockets, which burn through fuel quickly, fusion rockets could maintain a steady, continuous acceleration. This constant push would allow spacecraft to gradually build up speed, reaching incredible velocities over time. For deep space missions, this continuous acceleration is a game changer. With current chemical rockets, a spacecraft reaches its top speed and then coasts, relying on momentum to reach its destination. But with fusion propulsion, a spacecraft could maintain continuous acceleration, gradually increasing its speed and cutting travel times to distant planets and beyond. This opens up a new world of possibilities for interplanetary and even interstellar missions. Exploring beyond our solar system. The most exciting potential for fusion propulsion lies in its ability to propel spacecraft to other star systems. The idea of traveling to another star, exploring planets around distant suns, and even searching for habitable exoplanets becomes increasingly possible with fusion propulsion. The prospect of reaching Alpha Centauri, the closest star system to our own, becomes a tangible goal. One ambitious concept for fusion-powered interstellar travel is the Breakthrough Starshot project. The idea behind Breakthrough Starshot is to send small, lightweight probes to Alpha Centauri at a significant fraction of the speed of light. These probes would be powered by lasers and propelled by sails, but the underlying technology for fast space travel could one day rely on nuclear fusion. While Breakthrough Starshot is still in its infancy, the notion of using fusion to travel between the stars has captivated scientists for years. The fusion-powered spacecraft could eventually be used to travel to the nearest exoplanets, many of which are located within the habitable zone, where liquid water could exist. The discovery of potentially habitable exoplanets has raised hopes of finding another Earth-like world where humans could live. But before we can reach those planets, we must first figure out how to travel to them. Fusion propulsion might just be the key to making interstellar exploration a reality. Challenges of fusion. Propulsion. Engineering and safety. While the promise of fusion-powered space travel is enticing, there are significant challenges to overcome before we can harness the power of fusion in space. One of the most difficult aspects of fusion propulsion is creating the extreme conditions required for fusion reactions to occur. On Earth, scientists are working on achieving these conditions through methods like magnetic confinement and inertial confinement. These methods use powerful magnets or lasers to heat and compress plasma to the point where fusion reactions can take place. In space, however, the environment is even more challenging. Spacecraft would need to carry reactors capable of producing these extreme conditions and sustain them over long periods. Moreover, space engineers would need to design systems that can operate safely in the harsh conditions of space travel. Unlike traditional nuclear reactors on Earth, which are fixed and protected, fusion reactors in space would need to be extremely robust to survive the rigors of interplanetary or interstellar travel. Safety is another key concern. While fusion produces much less long-lived radioactive waste than fission, the process still creates some waste. and malfunctioning reactors could pose significant risks. Engineers will need to ensure that fusion-powered spacecraft are safe, reliable, and efficient. As humanity inches closer to harnessing nuclear fusion for space propulsion, the potential of this technology continues to astound and excite. But even as scientists and engineers make breakthroughs in fusion technology, the challenges that remain are daunting. Despite the promise of near-limitless energy and faster-than-ever travel, the path to using fusion as a reliable propulsion method in space is full of obstacles, both technical and theoretical. The physics behind fusion propulsion. To truly understand the significance of fusion propulsion in space exploration, we must first explore the physics behind it. Nuclear fusion occurs when two atomic nuclei, typically isotopes of hydrogen, collide and combine to form a heavier nucleus, releasing massive amounts of energy in the process. This is the same reaction that powers stars, including our Sun. In the Sun's core, hydrogen atoms fuse to create helium, releasing energy that powers the Sun and sustains life on Earth. The immense energy produced by fusion reactions is what makes fusion propulsion so compelling. In theory, fusion could provide spacecraft with a vast amount of energy, far beyond what chemical rockets can achieve. A fusion-powered spacecraft could travel much faster and farther, dramatically reducing travel times for missions to distant planets in our solar system, and even to exoplanets in other star systems. The energy released by fusion reactions is millions of times greater than the energy from chemical reactions, making it the ideal candidate for the next generation of space propulsion. However, the challenge lies in achieving and controlling the extreme conditions needed for fusion to occur. In the Sun, these conditions are naturally present: intense pressure and temperatures of around 15 million degrees Celsius. Recreating these conditions on Earth, let alone in space, is one of the most significant hurdles in achieving controlled fusion. To do so, scientists have to heat the plasma, the superheated, electrically charged gas where fusion reactions take place, to temperatures high enough to overcome the electrostatic repulsion between positively charged atomic nuclei. Magnetic confinement and plasma containment. One of the most promising methods for achieving controlled fusion on Earth is magnetic confinement. This technique uses powerful magnetic fields to trap and contain the plasma, preventing it from touching the walls of the containment vessel. The most well-known magnetic confinement device is the tokamak, a donut-shaped reactor designed to hold plasma in place using magnetic fields. The ITER, International Thermonuclear Experimental Reactor, project in France is the world's largest and most ambitious fusion project, using a tokamak to demonstrate the feasibility of nuclear fusion as a large-scale energy source. In space, magnetic confinement for fusion propulsion would be far more complicated. While it works on Earth because we can create stable conditions within a controlled reactor, space presents a whole new set of challenges. Spacecraft must operate in a vacuum, and maintaining the extreme temperatures and pressures required for fusion would be difficult without the protection of Earth's atmosphere. Furthermore, the magnetic containment fields would have to be highly efficient and able to work in the vacuum of space, far from the Earth's protective magnetic field. Inertial confinement. The laser approach. Another method that could be used for fusion propulsion is inertial confinement, which involves using powerful lasers to compress a small pellet of fuel to the point where fusion occurs. The National Ignition Facility, NIF in California, has made significant strides in this area, using lasers to create the extreme pressures and temperatures necessary for fusion to take place. While this technique has shown promise for energy production on Earth using inertial confinement in space for propulsion would present its own challenges. One of the major issues is the need for extremely powerful lasers capable of compressing fusion fuel on a spacecraft. These lasers would need to be compact, efficient, and capable of operating in the harsh conditions of space. The amount of energy required to initiate fusion through inertial confinement is immense, and ensuring that the lasers remain stable and operational over long durations of space travel is a significant engineering challenge. Sustainable fuel for long-term space missions. Another intriguing aspect of nuclear fusion in space is the fuel source. The primary fuel for fusion reactions is isotopes of hydrogen, deuterium and tritium. Deuterium is relatively abundant and can be extracted from seawater, while tritium is rarer but can be bred from lithium, which is also available on Earth and potentially on the Moon or asteroids. This makes fusion propulsion a more sustainable option for long-term space missions compared to traditional chemical fuels. In the near future, if fusion reactors could be established in space using these abundant fuels, the cost of launching missions would be significantly reduced. Instead of relying on massive amounts of fuel launched from Earth, spacecraft could be refueled using resources found in space, making deep space exploration more feasible and sustainable. One of the most exciting possibilities is using water ice, which is abundant on moons and asteroids, as a fuel source. Water can be split into hydrogen and oxygen through electrolysis, with the hydrogen serving as the fuel for fusion. If we can establish fusion reactors in space using these readily available resources, we could dramatically reduce the amount of material needed to be launched from Earth, making long-term missions to distant planets and even other star systems more achievable. The roadblocks and risks of fusion propulsion. However, despite the potential of nuclear fusion, there are many roadblocks and risks associated with fusion propulsion technology. As we discussed earlier, creating and maintaining the extreme conditions needed for fusion to occur is incredibly difficult. Fusion reactors require precision engineering and complex technology to ensure that they operate safely and efficiently. And these systems would need to function flawlessly over long durations of space travel. Additionally, there are significant safety concerns that must be addressed. While fusion itself is far cleaner and safer than fission, the reactors still produce energy at a scale that can be dangerous if something goes wrong. For example, the potential for a malfunction in the reactor could lead to catastrophic consequences. Spacecraft operating in the vacuum of space would need to be equipped with fail-safe mechanisms to prevent any fusion reactor from malfunctioning and causing damage to the spacecraft or crew. The potential for radiation from the fusion reactions is also a concern. While fusion produces far less harmful radiation than fission, it still releases neutrons and other high-energy particles. Scientists and engineers will need to develop materials and shielding capable of protecting both the spacecraft and the crew from these radiation hazards. Interstellar travel, the final frontier. The ultimate dream of fusion propulsion is the possibility of interstellar travel, the ability to travel between star systems, perhaps even reaching planets orbiting stars outside our own galaxy. The energy potential of fusion could make this dream a reality. If we can achieve continuous acceleration with fusion propulsion, spacecraft could travel at a significant fraction of the speed of light, allowing us to reach distant exoplanets in just a few decades. One of the most famous theoretical concepts for interstellar travel using fusion propulsion is the Icarus project. This concept envisions a fusion-powered spacecraft capable of reaching 10% of the speed of light, making the journey to Alpha Centauri, a neighboring star system, possible in just 40 years. While the Icarus project remains speculative, it offers a tantalizing glimpse of what the future of space exploration might look like if we can crack the code of nuclear fusion propulsion. The idea of interstellar travel has fascinated humanity for centuries. From the earliest days of science fiction to the latest cutting-edge research, the dream of reaching distant stars has been a driving force behind our scientific endeavors. However, to make this dream a reality, we need to break through the limitations of current technology, and the key to this breakthrough may lie in nuclear fusion. While we've only just begun to scratch the surface of fusion propulsion, its potential to revolutionize space exploration is nothing short of extraordinary. What makes fusion so captivating isn't just its potential for energy generation on Earth. It's the possibility that it could allow us to transcend the boundaries of our solar system and venture into the cosmos like never before. Fusion-powered interstellar travel, the holy grail of space exploration. Imagine a spacecraft, powered by the unimaginable energy of fusion reactions, capable of reaching speeds that bring other stars within our reach. Instead of waiting for decades to reach the outer planets, We could cross vast interstellar distances in a matter of years. The dream of visiting exoplanets, planets orbiting distant stars, becomes tangible, no longer confined to the realm of science fiction. But achieving this would require more than just incremental improvements in propulsion technology. To travel to stars like Alpha Centauri, which is over 4.3 light-years away, we need spacecraft that can travel at a significant fraction of the speed of light. Currently, the fastest spacecraft we've built would take over 70,000 years to reach Alpha Centauri. But fusion propulsion could change that, even at a modest 10%. Of the speed of light, a fusion-powered spacecraft could make the journey in about 40 years. The potential is so vast that Project Longshot, a theoretical interstellar mission, was proposed in the 1990s with the aim of sending a probe to Alpha Centauri using fusion-powered propulsion. While the project remains theoretical, the concept it presents is a vision of the future, one that could very well become a reality in the next few decades if we make the right advancements in fusion propulsion technology. Fusion rockets. Continuous acceleration for long-distance missions. One of the most remarkable aspects of fusion propulsion is the concept of continuous acceleration. Unlike chemical rockets, which provide short bursts of speed and then coast, fusion-powered spacecraft could accelerate constantly, gradually building up incredible velocities. This would allow for sustained long-term travel across vast distances, which is critical for interstellar missions. In a fusion rocket system, the energy produced by fusion reactions would heat a propellant, such as hydrogen, and expel it at very high speeds, creating thrust. The continuous acceleration would allow spacecraft to reach speeds far beyond what is possible with chemical propulsion. This continuous thrust would make missions to distant planets within our solar system, and even far beyond, feasible in a fraction of the time it would take with traditional propulsion methods. While the concept of a fusion rocket is still in the theoretical stages, researchers are developing various approaches to harness fusion energy for space propulsion. One promising design is the direct fusion drive, which would use the fusion reaction itself to generate plasma that could be expelled at high speeds, creating thrust. The advantage of this design is its simplicity and the potential for far greater efficiency than traditional chemical rockets. With fusion propulsion, spacecraft could accelerate for years, reaching unprecedented speeds and exploring the farthest reaches of space. Fusion and the search for habitable worlds. One of the driving forces behind humanity's desire to explore space is the search for other habitable planets. As our own planet faces increasing environmental challenges, the idea of finding a new home for humanity has become a pressing priority. While we have already discovered thousands of exoplanets, many of which may have the conditions necessary for life, traveling to these distant worlds presents an enormous challenge. Fusion propulsion could open the door to a new era of exploration, where the dream of colonizing exoplanets becomes a real possibility. Instead of waiting hundreds or thousands of years to reach distant star systems, fusion-powered spacecraft could take us there in a fraction of the time, allowing us to study these planets in detail and potentially establish colonies on worlds that might one day support life. The road to fusion. Propulsion. Key challenges. As promising as fusion propulsion is, the road to achieving it remains fraught with challenges. The extreme conditions required to sustain fusion reactions, temperatures in the millions of degrees and intense pressures, must be replicated and maintained in a controlled environment, which has proven to be one of the most difficult tasks in modern science. Current fusion reactors like ITER, International Thermonuclear Experimental Reactor in France, are making significant strides in replicating the fusion process. But we are still far from achieving the sustained, self-sustaining fusion reactions necessary for space propulsion. While breakthroughs are being made, creating a reactor capable of withstanding the harsh conditions of space travel is an entirely new challenge. For a spacecraft to carry a fusion reactor and harness its power for propulsion, the technology would need to be miniaturized, made more efficient, and able to operate in space for extended periods. Engineers would also need to design advanced cooling and shielding systems to protect the spacecraft from the intense radiation and heat generated by the fusion process. These systems must operate reliably even in the unforgiving environment of space. The promise of abundant fuel. Isotopes of hydrogen. One of the key advantages of nuclear fusion as a fuel source for space travel is the availability of fuel. Unlike chemical rockets, which rely on finite resources like liquid hydrogen or kerosene, fusion uses isotopes of hydrogen, specifically deuterium and tritium, as fuel. Deuterium is abundant in seawater, and tritium can be produced from lithium, which is readily available on Earth and potentially even on the Moon or asteroids. This accessibility of fuel makes fusion propulsion particularly attractive for long-term space missions. If we can establish fusion reactors in space, using resources found in space itself, we could significantly reduce the amount of material that needs to be launched from Earth, making deep space exploration more sustainable and feasible. The use of space resources for fuel could eliminate the logistical challenges of transporting vast amounts of fuel from Earth and drastically cut mission costs. The vision for intergalactic exploration. The ultimate goal of fusion propulsion is to make intergalactic exploration a reality. While traveling to distant stars like Alpha Centauri is within reach, the next step would be exploring the farthest reaches of our galaxy, the Milky Way, and eventually other galaxies entirely. With fusion-powered spacecraft, we could explore other star systems, examine exoplanets for signs of life, and push the boundaries of human knowledge like never before. The possibility of intergalactic travel, of sending missions to distant galaxies, might seem like science fiction, but fusion propulsion could make it possible. By reaching speeds close to the speed of light, spacecraft could cross the vast distances between galaxies in a human lifetime. This would revolutionize our understanding of the universe and our place within it. The future of fusion. Propulsion. A new dawn for space exploration. The promise of fusion propulsion is undeniable. While we are still in the early stages of this technology, the possibilities it offers for space travel are limitless. From faster missions to distant planets in our solar system to the potential for interstellar and intergalactic exploration, nuclear fusion has the potential to make the impossible possible. As research into fusion propulsion continues, we may one day look up at the stars and realize that the dream of exploring the cosmos is no longer a distant fantasy, but a future within our reach. The universe, vast and mysterious, could soon be ours to explore. As the sun sets on our current understanding of space travel, a new dawn begins to emerge, one where the distant stars and unexplored galaxies no longer feel out of reach. With fusion propulsion on the horizon, the limits of our solar system may soon expand far beyond what we ever thought possible. The key to this transformation is unlocking the power of the stars themselves, nuclear fusion. The transition from chemical rockets to fusion-powered spacecraft represents not just a technological leap, but a monumental shift in how we view the future of space exploration. Imagine a future where we no longer face the endless weight of decades-long space missions. A future where we don't just send robotic probes to the edge of our solar system, but where human beings travel to distant worlds, explore new star systems, and even plant the seeds of civilization on faraway planets. The implications of nuclear fusion propulsion extend far beyond simple fuel efficiency. They open up entirely new frontiers. For the first time in history, the impossible becomes achievable. Fusion-powered ships, colonizing the stars. As fusion propulsion technology progresses, the potential for space colonization will shift from fantasy to feasibility. One of the most thrilling possibilities for humanity's future is the colonization of exoplanets, planets orbiting stars beyond our own sun. Today, we have already discovered thousands of exoplanets, some of which lie in the habitable zone, the region around a star where conditions are just right for liquid water to exist. Planets like these could harbor life or become the future home of human civilizations. But before we can take the monumental step of colonizing other worlds, we must be able to travel to them in reasonable time frames. Enter nuclear fusion. Fusion-powered spacecraft could traverse the vast distances between star systems at a significant fraction of the speed of light. A journey that currently would take tens of thousands of years could be reduced to mere decades. This capability could open the door to a future where humanity is no longer confined to Earth, but is a spacefaring species, reaching the stars, settling on exoplanets, and perhaps encountering alien life along the way. The quest for Alpha Centauri and beyond. Let's consider the journey to Alpha Centauri, the closest star system to ours, just over 4 light-years away. With traditional propulsion, this journey would take over 70,000 years, far beyond the lifespan of any current spacecraft or human explorer. But with fusion propulsion, a spacecraft could potentially reach 10% of the speed of light, cutting the journey time down to a mere 40 years, a time frame we could feasibly work within for intergenerational travel. With this capability, Alpha Centauri could be our first target in the interstellar exploration race. Once we've achieved this monumental milestone, the next frontier will be the hundreds of billions of stars that inhabit the Milky Way alone. And beyond that, who knows? With fusion propulsion, intergalactic travel, visiting galaxies outside our own, becomes conceivable. Imagine humanity leaving its mark on countless star systems, each world a new chapter in the story of our species. The power of fusion, beyond space. Propulsion. But nuclear fusion's impact won't just be limited to interstellar travel. As humanity masters fusion, it will also revolutionize how we live on Earth and in space. The potential for near-limitless clean energy means we can finally break free from our reliance on fossil fuels, transitioning to an energy source that could power cities, industries, and even space colonies for centuries without harming the environment. Imagine colonies on the Moon, Mars, or even asteroids that are powered by fusion reactors, providing energy without the environmental impact that current energy sources impose. In the future, fusion energy could power everything, from life support systems in space to entire cities on Earth. With abundant fuel sources in the form of isotopes of hydrogen, the energy crisis could be a thing of the past. And as we begin to harvest resources from asteroids, the need to launch materials from Earth would be drastically reduced. Fusion and the search for life. A new chapter in astrobiology. Fusion propulsion also carries the possibility of opening the doors to alien worlds, planets with conditions similar to Earth. With the ability to travel to distant stars, we could one day discover life beyond our planet. Perhaps we will find other civilizations or even microbial life on exoplanets orbiting stars that are hundreds of light-years away. This new era of space exploration could lead to groundbreaking discoveries that change how we view our place in the universe. The discovery of life, especially intelligent life, would redefine humanity's understanding of the cosmos. It could provide answers to the ultimate question of whether we are alone in the universe. Fusion-powered spacecraft traveling to the farthest reaches of space could hold the key to uncovering these mysteries. The technological road ahead. While the promise of fusion propulsion's extraordinary, the road ahead is fraught with technological and engineering challenges. Achieving sustainable fusion on Earth has already proven to be an incredibly difficult task, and creating reactors capable of producing the power needed for space propulsion is an entirely different challenge. The conditions required for fusion, millions of degrees of heat, massive pressures, and the containment of high-energy plasma, must be perfected in compact, reliable reactors that can operate for years in the harsh environment of space. But as we continue to push the boundaries of scientific knowledge and engineering innovation, breakthroughs are happening. The ITER project, currently being constructed in France, aims to demonstrate the feasibility of fusion energy on a large scale. The success of ITER would mark a pivotal moment in the history of energy production and could be the first step toward creating fusion-powered spacecraft. The race to develop fusion propulsion for space travel is accelerating, with multiple organizations and nations working together toward this monumental goal. From NASA's advanced propulsion programs to private sector innovations, the next decade will likely bring us closer to realizing the dream of fusion-powered space travel. A bold vision for humanity's future. The future of humanity is undoubtedly intertwined with the continued exploration of space. As we stand at the edge of this new era, it is clear that fusion propulsion is the key to unlocking the next chapter in our cosmic journey. With the promise of near-light-speed travel, long-term space missions, and interstellar exploration, fusion propulsion could transform our future, enabling us to reach new star systems, find new worlds, and perhaps even encounter new forms of life. While there are still many hurdles to overcome, the potential for fusion to power space travel opens up a universe of possibilities. The universe, vast and mysterious, is no longer just a backdrop to human history. It is within our reach. The dream of traveling to the stars, once relegated to science fiction, could soon be a reality, all thanks to the power of nuclear fusion. The end.